Operational Properties Part 2. There's really not too much to this section. It has a bit of convolution, which covers some terms for the Laplace transforms that is very intrinsic to try to uncode. But the Laplace transform will make the work a whole lot easier. So what is actually the most difficult section really probably becomes the easiest, in that this section talks about trying to calculate the Laplace transform of a periodic, an integral that involves periodic piecewise intervals. Well, the interesting thing is that the definition for the Laplace transform is already defined on an integral. And so once we take the Laplace transform of that particular periodic interval, we just get a standard Laplace transform. And so the work is a whole lot easy. Well, they first begin with the derivative of a transform, and I had told you about this a couple of sections back where we talked about the transform of a derivative, which you just take the Laplace transform of whatever derivative. But this is like backwards. Here you're actually taking the derivative of a transform, and so when will you have to do that? Is in and of itself somewhat difficult to figure out. What happens is, if you look at number 3, if you look at the Laplace transform of a term that basically, this is how I get it, where I hadn't seen anything like that previously, because for the first translation, first and second translation, you got some kind of composition dealing with some e to the at times some other function. It could be times whatever function, doesn't matter. But notice here we don't have that. When you have, and this is like almost what they're begging, is that when you have the Laplace transform of a polynomial times a function, then what they're saying here is you can simplify that. You can find out what that is by just decoding that to be the derivative. So if you have the Laplace transform of t to the n times a function, where in that it doesn't really even tell you that it's the derivative. Now what they're begging, and I think is this, is that if you see the combination of the Laplace transform of some polynomial times some function, doesn't matter what f of t is, then they're saying you can break that down by a derivative. Now, whatever that power of t is based on the formula in terms of how you want to break down whatever derivative. So if it's t to the first power, then you're just dealing with the first derivative. If it's t to the second, then you're going to do the second derivative on the Laplace transform. So here, this is t to the first power, and I'm going to do that because that's pretty easy. So based on this formula, this is -1 to the first power times just the first derivative of the Laplace transform of cosine of 2t. So we first break down the Laplace transform of the cosine 2t. Now this is -1 times the derivative and this is the derivative of the cosine of 2t, the Laplace transform of cosine of 2t. And I guess I can make that a little bit more presentable. So the Laplace transform of the cosine, remember if it's cosine, then the s goes in the numerator. So this is s over s squared plus 4. So now I'm taking the derivative of this. So don't forget the -1 sitting out there. So for this derivative, we use the quotient rule. So the derivative of the numerator is 1 times our denominator minus the numerator times the derivative of the denominator all over our denominator squared. And so we simplify that. Again, the -1 sitting out in the front. So it's s squared plus 4 minus 2s squared. So that's minus 2s squared plus s squared is just negative s squared plus 4 over s squared plus 4. These are unlike terms, so please don't try to cancel anything out. And it just shows me what you don't know about arithmetic. So just run the negative through. So we have s squared minus 4 all over s squared plus 4 to be squared. And that's it. There's a formula on the formula sheet. I don't use formula, but you can look at that and you can just match that information up. The same thing here. This guy just used that formula sheet. Who wants to go through and look? This is, you got to find two derivatives, the first derivative and the second derivative, and it's like quotient rule twice. So use the formula sheet, right? That's what I would do. Use that and you get the answer. All right. Try your hand at that. I'm not going to mess with that. I want to keep life as pleasant as possible. You say life as pleasant as possible, and the first word that pops up is convolution, which is like a bunch of stuff that's messy, right? Yeah. Transforms of integrals. So if functions f and g are piecewise continuous on the interval from 0 to positive infinity, then a special product denoted by the convolution of f and g is defined by this integral. The convolution of f and g is the integral from 0 to t of f of tau times g of t minus tau d tau. Oh, tau? Okay. Now, the really cool thing about that is if you have the convolution of two functions, which basically is that this is the integral, and that's what is defined as. If you take the Laplace transform of this special product, then that just equates to the Laplace transform of the individual functions, which is very easy. Now, if you have the Laplace transform of the integral here of the function, then it's understood to be, the first function is f, is understood to be 1. And then times the Laplace transform of some f of t, right? So the Laplace transform of 1 would give you 1 over s. So at any rate, this is just the Laplace transform of 1 times the Laplace transform of t to the third, which is 1 over s times 3 factorial, which is 6 over s to the fourth. And you can just write that as 6 over s to the fifth. Oh, a lot of space there. I don't think all that comes up. Just gonna leave it alone. So this is the Laplace transform of e to the negative t times the Laplace transform of e to the t times cosine t. So this is 1 over s plus 1 times this cosine, Laplace transform of cosine is s over s squared plus 1. But only for this one, this is the first translation theorem, s goes from s to s minus 1. Only for the first part. Well, only for the second part, excuse me. The first part is by itself. So this result then is 1 over s plus 1 times, here where I see s, I'm going to write s minus 1 over s minus 1 to be squared plus 1. And you just write that all as one term, s minus 1 over s plus 1 in parentheses times s minus 1 to be squared plus 1. And you can simplify that. I'm just going to leave it just the way it is. Now this, you don't see it, but you go back to, see, where did they put it? Right here. That problem looks like this, the Laplace transform of an integral. It's two things going on. It's the Laplace transform of 1 times this function, this integral for f. So this is the Laplace transform of 1 times the Laplace transform of e to the t, right? This tau is on an interval from 0 to t. So this is just 1 over s times 1 over s minus 1. And you can just write that as 1 all over s times s minus 1. This is the Laplace transform of e to the negative t. Now this is 2 guys here times the Laplace transform of cosine t. So this is 1 over s plus 1 times, for that Laplace transform of cosine, that's s over s squared plus 1. And you can just say that this is just s all over s plus 1 times s squared plus 1. And no need to try to simplify that. Just leave that the way it is and keep moving. What is this? This is the Laplace transform of t times the Laplace transform of e to the t. That's how that the definition for this convolution is defined. That tau is within t. That's all you need. And so this is 1 over s squared times 1 over s minus 1. So this becomes 1 over s squared times s minus 1. And I mean, that's basically about it. This section was pretty good. All the work really is in the previous sections. And so not too much going on here. And that was 31, then number 29. Number 27. That looks about right. And That's number 25. Okay, that's good. Number 23. Yeah. And then we did the first one, and that was that derivative of the transform. Okay. Well, that's about it. Thank you.